Previously, we developed this arc length function, and there's an interesting result that comes from this arc length function, and that's what's called the arc length differential. So first of all, let's take the derivative of this function. Now this is interesting because this is a function that's defined as an integral. So I'm interested now in what is the derivative of s with respect to x. Now if you look at that, that looks a lot like the fundamental theorem of calculus part 1. You've got a function defined as an integral from some constant up to the variable, and then we're turning around and differentiating that function. And the fundamental theorem says what you're left with is this integrand evaluated at x. That's by the fundamental theorem of calculus part 1. Now recall from Calc 1 that we defined a differential, ds, would be the derivative of s with respect to x dx. So that's just the definition of a differential on any function. And in this particular case, we know ds dx is square root of 1 plus f prime of x squared, and then dx. But this thing looks kind of familiar, right? This looks like part of our integral for arc length. It looks like the part without the integral symbol, right? This thing here we call ds is what we call the arc length differential. And one immediate benefit of this is that now arc length, remember, which was the integral from a to b square root 1 plus f prime of x squared dx, we could just say is the integral from a to b of ds. Now, practically speaking, this isn't very helpful. You still need to know what ds is in order to calculate arc length. But more generally, mathematically, we like this type of expression because it says exactly what it is it's doing. Remember, an integral is a summing. It's a type of summing. It's an infinite sum, right? As the norm of the partition shrinks down to 0, there's more and more things that are being added up. So in some sense, conceptually, this is a sum of a bunch of little infinitesimally small lengths. And when you add up all the little lengths, you get the length. So this statement mathematically says length is the sum of little lengths. And so we like this type of notation, just from a conceptual standpoint. Another benefit to this type of notation is this can change a little bit, right? If it's a function of y, this is f prime of y dy. Later on, we'll look at a different type of function called a parametrically defined function, and this expression changes a little bit. We'll look at polar functions. In polar, this expression changes a little bit. In Calc 3, you'll look at what are called vector-valued functions. This will change a little bit. But we could always say that it's the integral of ds. What changes is the details of that little arc length differential. And we'll look at other things in here and in Calc 3 where we could express this in some sort of little infinitesimal piece. Surface area is the summing of a bunch of little surface areas. Volume is the summing of a bunch of little volumes. And so we can have this little differential notation as a shorthand for what we're doing in all these different applications of integration.